So the quizzes that I put up, the last few quizzes, are pressure conversions, the PV equals NRT stuff, and stoichiometry with gases. All of this stuff we've gone over. So I'll go over these quizzes first, and if there's anything else you want me to go over, let me know. But the quiz is just like these conversions. So let's say I did 28 here, 652.5 millimeters of mercury. Okay, so this is number 28. For atmosphere. Inches of mercury at PSI. So to convert for all of these, we're in millimeters of mercury. This is number 28. So I'm going to put millimeters of mercury down here. And if I want to put that in torr, I have to put torr up here. And that's these numbers that I'll give you on the test. So 760 torr is 760 millimeters of mercury. So it's just because millimeters of mercury and torr are the same. So if I wanted to do atmospheres, that means I want atmospheres on top. So I've got 760 millimeters of mercury, then 1 atmosphere. So that's just 652.5. Divided by 760. 0.859. Next one is inches of mercury. So 760 for millimeters of mercury. Inches is 29.92. Six 52.5 times 29.292. 25.69. And then for PSI, Seven 60 millimeters of mercury, PSI is 14.7. Those are easy, right? Okay, kind of a quiz for that one. For the PV equals nRT ones, so I have a good break. I was sick over break. Sample of gas has initial volume. Okay, so this is where you go. R will always be the same. Meters, atmosphere, Kelvin. Okay, if we read this problem, initial volume of 12.2 liters. Initial pressure, 1.22 atmosphere. It says constant temperature. So this is constant. It doesn't even mention moles, so consider those constant. It tells you final volume is 10.1. And you're asked for what's the pressure. Start with that. You want everything changing on the left and everything not changing on the right. It happens to already be the way we want it. Pressure and volume is on the left. So this is pressure 1, volume 1, pressure 2, volume 2. And then you solve. We're solving for P2, so a little algebra gives me that. So 1.22 for P1, 12.2 for V1, 10.1 for V2, and that should solve it. 1.22, 12, 2, divided by 6.47. Okay, question 2 on here. What do we have? 44.5 milliliters. Um, 26.6 to 88.2. But I have to convert these to Kelvin. 273.15. So I'm keeping those, so 299.8. T1 equals 299.8 Kelvin. 5, 3, 4. So those are temperatures. And it's asking for a final volume. That's not mentioned, and that's not mentioned. So we need temperature and volume on the left, and everything else on the right. So a little algebra gives me this. These are the things that are not changing. These are changing. We set up that. And we're solving for V2. So a little algebra gets me multiply both sides by T2. Volume 1. Volume 1, temperature 2. Temperature 1. .5 times 361.84. Yeah. It's going to be in milliliters. Yeah, I did my significant figures a little bit. That was 53.5. I only put 3 of these in here. There are more. What do we got? 1.01 moles of gas. 33.6 liters. Liters. 1.22 moles of gas are added. Notice this is 1.01 plus 1.22. 1.22 moles are added. So we have to add those together. So we have 2.23 moles. The things that are not mentioned are pressure and temperature, so those stay constant. So it's moles and volume are changing. So a little algebra gets me here. So V1, N1. We're solving for V2, so a little algebra, multiply both sides by N2. And volume 1. liters. Moles N2 is 2.23. N1 is 1.71. $74.2. More problems like that, if you wanted more, is 33 through 40. But there's lots more variations on this. It's just two things changing, everything else not changing. There's more variations in there. I didn't even do Thanksgiving. I didn't even go home because I didn't want to get everybody sick. So I've just been holed up in my apartment, being miserable. Okay, still geometry with gases. Yes, I put a few of these up. All right. What volume of O2 is needed to produce 36? Let me write some of this down. We need to produce pressure is okay, you need this. Six oxygens. There should be a two. Zero. Okay, so we're going to find the moles of O2. Al2O3 Al2O3 is so you find the grams per mole for Al2O3, that's what goes here. There's 1 mole. This is the mole ratio up here. So 2 of those to 3 of those. And that's going to give you the moles of O2. So that's what we're finding here. 34.6 times 3 divided by 101.961 divided by 2. 0.509 moles of O2 are what we need to get 34.6 grams of Al2O3. And now we use and we're solving for volume. What volume of O2? Volume equals nRT over V. And we've got for moles 0.509 R 206. Temperature 375 over so divide both sides by P, we get here 1.24 atmospheres. So 0.509 times 0.08206 times 375 divided by 1.24. Okay, 12.6. That's going to be the numbers. I think my answer key is wrong because that 2 wasn't there. 12.6. Yeah. I'll give you the R number. Asking for volume. So this equation solid. I already see the mistake. 6 of those. That answer key is going to be wrong too. What volume of Na3N2 Na3N is H2. Two of these, so one of those. $17.5 divided by 82.976 divided by 2. That's how many moles. There is a temperature and pressure on here. Pressure is 285. To solve for volume, so the moles was 0.101, R is 0.08206, temperature is 285, and the pressure is 0.927. 0.101 times 0.08206 times 285 divided by 0.927. That one. I'll check the rest of these. 6 Li, 6 Li, and okay, notice all of these ask what volume. We find the moles and then we find the volume. 4 H's. That's not L-C. is a variation on this. One variation on this is, it's not in my quizzes, but if you're given grams, you're asked for the volume. Instead of being asked for the volume, you're given the grams. So this is number 90. Yeah, 93. So be able to do this as well. It's just going the other direction. Now it's going to say N3. They, that's their typo. That's what I get for copying you. NA3 in 6NA. Gas. That's a solid. That's a solid. Okay. Since they have a typo, you just make it while we're standing here. Liters. Change this a little bit. Let's see what that does. Don't do 93 because they have a typo. So going the other direction, it looks like this. Reduced 12.5 liters up into So now we're going to use PV equals nRT first. Let me write the reaction down. That's a solid. That's a gas. This is a solid. Okay. We're solving for N here, so PV over RT equals N. And pressure is 2.35. Volume is 12.5 liters. 0.08206 for bar. Temperature 386. So moles we're going to get 2.35 times 12.5 divided by 0.08206 divided by 386 moles of N2. So now going the other way, 0.927 moles of N2 moles of N2 to 2 moles, 1 mole of N2 to 2 moles Li3N, and 1 mole Li3N is 34,830. 34,830. And that'll give us the mass of the heat. This should say Li. I got sick twice this semester. All right, 64.6 is what I see. And we got some answers. So be able to do one like that too, just going the other direction. Look at else. Did I have heat capacity up there before? I think I made that up over break too. This one. This many grams of copper, initially at 22.5 degrees C. What is the final temperature? Absorbs 6 kilojoules of heat. So what is the final temperature? You need for this, and I'll give you these on the test, this list, copper 0.385 joules per gram per degree C. Joules per gram per degree C. Set it up like that. And then grams. Grams, that cancels the grams. And then you need delta T here, which is T final minus T initial. T initial is 22.5. So you solve the temperature final here. The way to do it, divide by 0.385 and divide by 25.6. T initial is joules per gram per degree C. Divide by divide by that, and divide by that. Yeah. Why did I write it this way? That's just the way I keep it in my head. Heat capacity times grams times the delta T tells you the amount of joules. What about it? Well, I started with this, and now I'm going to divide both sides by 0.385 and 25.6, and that's how I got here. Questions?
Yeah, it's supposed to be kilojoules at the, or
Oh yeah, I can convert the kilojoules, you're right. Let me neaten this up a little bit. I still feel like my head is in a jar. Let me straighten this up a little bit. It's always heat capacity times mass times delta T energy transfer. I'm going to do heat capacity first. Joules per gram per degree C. I'll just write it like that. Heat capacity times the mass, which is 6 C, and then the delta T, which is final minus initial. Since we're trying to find final, I have to write it this way. Temperature final minus the initial was 22.5 degrees C. This was grams. And that equals 4.46. Yeah, I didn't convert it. 4.46 kilojoules is joules. There, I converted the joules, the kilojoules to joules. Did I lose you again? The heat capacity times the mass times the change in temperature tells you how many joules were transferred. If you have this many grams of copper and the temperature changed by this interval times the heat capacity, that tells you how many joules it took to make that temperature change.
If I did change the joules to joules, right? I mean, that makes more sense.
And since this is in joules per gram per degree C, I changed the 4.46 kilojoules to 4.460 joules. Okay, so I'm just solving for temperature final here. If I divide both sides, 385, those cancel out. We're down to temperature final equals 22.5. So we're that far with algebra. I've started dropping the units off here. You guys with me now? All right. And one more thing I can do, I can add 22.5 to both sides. So temperature final equals 4460 divided by 0.385, 25.6 plus, and that'll solve for temperature final. I bet my answer key is wrong for some reason. 4460 divided by 0.385 divided by 25.6. Something huge, what, 475? Answer key is right. 475. You guys follow that? I did that a little sloppy, but does it make sense? I'll do it. Let's do that one. The next one in here is 47.8 grams of iron, initially at 20.7 degrees C, is final. Absorbs 98.7 joules. Again, we need the heat capacity. Iron is 0.449. So I'll start by setting it up by saying heat capacity doing this iron times mass times delta T, energy, in this case joules. Heat capacity, the mass is 47.8 grams. The delta T is T final minus 20.7 equals, and what was transferred is 98.7 joules. To solve for TF, so divide both sides by 0.449 and 47.8, and then add 20.7 to both sides. .7 divided by 0.449 divided by 47.8. That plus 20.7, I get 25.3. Yay, 25. The variation on this. How much heat is required? So this is question 4. How much heat? To heat 23.6 kilograms of lead. We need heat capacity of lead is 0.128. So this one we're going to go 0.128 joules per gram per degree C. Mass kilograms, we have to go from kilograms to grams. So we need that conversion. Grams. And then the delta T, which is T final minus T initial. Final is 35.0. And initial, and that'll tell you how much. 35 minus 23.5. So the delta T is 11.5. This times 1,000 is 1, 2, 3. So it's that many grams. So that's that. 0.128 times 23600 times 11.5. The calculator says that'll be in joules, because this is joules. So kilograms cancel, this is a degree C. So kilograms cancel, and then grams cancel, and then degree C cancel, so in joules. We have 3 significant figures, 3 and 3, so really I'm just keeping that. So that works. You can also do that would be true. those would work. Let's see if you want to put it. That's the one I've got there. Probably we should review calorimetry. Can we do this? Not if we do that. So this wants to know the delta H of the reaction. Find delta H of the reaction. Okay. The initial temperature of the solution, and then there's a final temperature of the solution. You're also given that's the density of the solution, and you're told to use heat capacity of the solution. So there's all your information. Find heat reaction in kilojoules per mole of magnesium. You have 100 milliliters of solution. If this is the density, grams of solution per 1 milliliter solution. So this grams per milliliter is what I've got here. So that's going to tell you how many grams of solution you have. So 100 times 1.01 is 101. So that's how many grams of solution we have. So now we have the heat capacity, we have the grams, and the delta T is going to be final minus initial. So delta T equals 28.6 minus 22.2, which is 6.4. All right, so now we have heat capacity of the solution, we have mass of the solution, and we have delta T for the solution, and that's going to give us some number of joules.
What is the question
delta H of reaction in kilojoules
Oh, I
per
see
mole.
that. Okay.
It's right in the middle of the paragraph. So our heat capacity we're using is 4.11. Our mass is 101. And our delta T is 6.4. 4.11 times 101 times 6.4. So we have 6, 5, 6, 7, 4 joules. We'll just keep it 3 significant figures. So 2660 joules, which is 2.66 kilojoules. We need kilojoules per mole. Left one thing out. 0.252 grams. We have that many grams of the mg. So we just need to find out how many moles that is and then divide. mg. mg, 24.31. And we decided we have 2.52 grams of energy. So how many moles of energy do we have? 252 times 24, 31. 252 divided by 24.31, 0.014 moles of energy is what we have.
I'm just trying to. You got that 2.52 grams. Where'd you get that 2.52? I mean,
That's in the problem. I just didn't write it down. It's in the problem. It says you have this many grams of energy. I just didn't write it down at the beginning. So you leave that off to the side for a while. And you do your calorimetry to find what kilojoules. So now that I have the kilojoules, I'm just going to divide that by the number of moles.
so is that mass supposed to be 1.01?
Yes. No, 101. We had 100 milliliters of solution. So we found this for the grams. 100 milliliters of solution ends up weighing 101 grams.
So we have to solve it with the 101 first before we can look at the solution of magnesium.
Yeah, it is a solution of magnesium. The solution of magnesium.
Yes, I mean like we have to solve the kilojoules before we can.
Well, we solved this first, so we could put it in here.
Yeah.
This was given, and this was calculated from the deltas.
Yes, I understand. But my question is, how come you needed to look for the 0.252, like grams?
We only need that to find. We only need that to find out how many moles are present,
Okay.
which is an
We're just
afterthought.
looking for the general solution first, and that's what we found the kilojoules.
Well, general solutions. I mean, you find out how many kilojoules were transferred first.
Is that 4.31? That's going from the periodic
this. That's from the periodic table. That's grams per mole from the periodic table. Everybody else okay? I feel like my head is in a jar, so I can't really hear it either. You guys follow this? So you use the density to find the grams. You use the heat capacity that's given. That's given in the problem. This you calculate from temperature final and temperature initial. Then you can calculate the joules that were transferred. And then you stick that on the back burner for a minute, and you go back over here and you go, this is how many grams of Mg I have. So how many moles is that? It turns out to be this many moles. And then the final step is to get it in kilojoules per mole. 2.66 kilojoules. 0.0 moles. That'll give us kilojoules per mole. 2.66 divided by 0.0104. 255.7, 256 kilojoules. And 266. The fact that it's exothermic tells you that it's negative. Do that wrong. 2.66 divided by 0.0104. 256. Yeah, negative 256.
How is it negative?
Variation on the calorimetry. Notice this was what you put in the calorimeter here was some solid Mg put in 100 milliliters of solution. The other variation two solutions poured together. So this one looks slightly different. So this one. 1.05 molar AgNO3 is mixed with 'initial temperature is 23.4. Final temperature is 27.8. We see This means we're going to need the moles of AgNO3 at some point. Kilojoules per mole. Per mole of what? AgNO3. So first we've got to find out the heat transfer that occurred. You're also told density of the solution once they're poured together. And heat capacity of the solution, you're told, is 4.22 joules per gram per cc. All right. 50 milliliters of this plus 45 milliliters of this. You have 95.0 milliliters of solution. That makes sense? It's different from just taking this that we had before, because this time we had two solutions that we poured together, and they added up together as 95 milliliters. 95.0 milliliters, 1.11 grams or 1 milliliter. So the grams of solution we have 95 times 1.11, we have 105 grams of solution. There's our grams. Here's our heat capacity of the solution. We're also going to need a delta T. Delta T equals temperature final minus temperature initial. Final is 27.8. Initial is 23.4. 27.8 minus 23.4. So now we have delta T, we have grams, and we have heat capacity. So now we can figure out how much energy was transferred. 4.22 for heat capacity, 105 for grams, and 4.4 for delta T. 4.22 times 105 times 4.4. I guess we only keep two significant figures here because of this. 1900 joules or 1.9 kilojoules. So now we have our kilojoules. One more thing, we need to know the moles of AgNO3. Moles of AgNO3, we have 50 milliliters, 1,000 milliliters is 1 liter, and then the 1.75 molar means 1.75 moles in 1 liter. That'll tell us the moles of AgNO3. 50 times 1.75 divided by 1,000. 0.0875. So our final point is 1.9 kilojoules, 0.0875 moles. So our kilojoules per moles is 1.9 divided by 0.0875. I guess that should really be 22. This is not just in case. better double check it since I've got an answer key up there. 4.22, 105, and that's 4.4.
Dr. Henry,
Yeah.
on the top right corner of the board, it says, I can tell it says 1,000 milliliters. Should it be 95?
55, yes.
Oh,
No, this should be 1.05. That's all that's wrong.
1.05.
Yes. It's 50 milliliters of 1.05 molar AgNO3. All the AgNO3 comes from that 50 milliliters. So I did do something wrong there.
So is that,
I used 1.75 instead of 1.05.
so that under the 1 liter, is that 1,000 or 100?
It's 1,000. 1 liter is 1,000 milliliters.
Okay, okay.
50 times 1.05 divided by 1,000. So this should be 525 moles. My answer key is still wrong. Nine divided by 0.0525 46. You okay with that? Did you follow it?
Lessons for chapter 2 and chapter 3 together, or are they separated? Okay, no, I see, no.
Yeah, it's chapter 9 and chapter 10 we're in. So the Hess law, the bond energy stuff will be there. I took off the use of formation.
So what?
Energy stoichiometry, general reaction stuff. Anything else y'all want to go over?
So what's all going to be on the test?
Everything is there. What's in these quizzes is going to make up the test. If you can do these quizzes, you should be ready for the test. And we just covered about half of it. So these that I haven't reviewed. Anything else y'all want to go? Kelly, are you doing any meetings?
Sorry?
You doing any meetings between now and Wednesday?
Yes, we're about to send out an announcement. We're going to have our meeting tonight instead of tomorrow. I had some weird scheduling conflicts this week, so we're going to meet tonight at 5 a.m. 136. Same place, same time as today instead of tomorrow. I'll send it
So,
over to you.
just focus on those quizzes, what's in there. And if you see any mistakes, I just found how many while we were standing here, so I want them to be correct. So